In this video, we're going to come back to the same example that we saw before, asking whether seeing a picture after or before reading ambiguous prose makes a difference for comprehension scores compared to seeing no picture at all. In the last video, we had finished up with this less than satisfying conclusion that at least one of the conditions is different from the others in terms of reading comprehension. The problem here is that we don't know which ones or which one are different, or by how much, right? It's possible that the difference is statistically significant, but not actually large enough to be practically important. We can't really address either of those questions yet. So we're going to do a follow-up test. This is called a post hoc analysis, but really that's just like a pretentious way to say that it's done after the main analysis. And the way that we're going to do this is that we're going to look at the groups two at a time. So the benefit of looking at them two at a time is that everything that we learned about t-tests works again, right? Because t-tests are appropriate for comparing two groups. When we wanted to compare three groups, before, after, and none, we had to use an f-test. But now as a follow-up, we can use t-tests to look at the groups two at a time. So the first thing here is the difference, which is just the difference of means. So I'm going to write this as y bar 1 minus y bar 2, and that's going to be whatever order they're listed here. So like here it says before minus after. So this is giving us the difference of the sample means for before minus after. Lower CL and upper CL, this is the 95% confidence interval for the long run difference in means. So like mu1 minus mu2, depending on which groups you're comparing. And then this is the two-sided p-value. So let's start by looking at before minus after. So if we compare before and after, there's a pretty big difference between these. This is why it's the first in the ordered differences report, because this is the largest difference between the groups. So the difference in means was 1.737. And then if we look at the confidence interval for that difference, see that the confidence interval does not include 0. So if the confidence interval doesn't include 0, that means it's not reasonable to believe that the true difference in the means, mu b minus mu a, is actually 0. This is confirmed by having the really small p-value here, so 0.0002 for the p-value. So together, these give us strong evidence that there really is a difference between the mean comprehension score for those who saw the picture before and the mean comprehension score for those who saw the picture after. We can also say something about the size of the difference, right? It could be as small as less than 1 point, or it could be as large as over 2.5 points. The confidence interval gives us that range. So this was the comparison for before minus after. This would be very similar for before minus none. The confidence interval doesn't include 0. It's slightly different. The estimate of the size, it looks like, is slightly smaller. And the p-value is a little bit larger, but overall our conclusion would be the same, that we have strong evidence that the mean comprehension score for before is not the same as the mean comprehension score for none. That before does seem to offer some benefit. Notice how that changes here. If we look at none minus before, the confidence interval does include 0, so that means 0 is a plausible value for the difference. It's reasonable to believe that there's actually no difference between seeing the picture after reading the text and not seeing the picture at all. This is consistent with the large p-value that we get, right? We have very weak evidence of a difference. Another way that we can see this information is in the connecting letters report. So notice it says here, levels not connected by the same letter are significantly different from each other. So before doesn't share a letter with either of the other groups. So this means that before is significantly different from the other two options, from none and after. But then none and after are both the letter B, so none and after are not significantly different from each other. So we don't have enough evidence here to say that those two treatments are actually different from each other. So far, we've just been doing simple t-tests for this, but there's actually a little bit of a problem related to type 1 error. So remember, type 1 error is when you make a decision to reject the null hypothesis when in reality the null hypothesis is true. So that would be saying that two of these conditions, before, after, and none, are different from each other, when in reality they have the same effect on reading comprehension. So remember, the significance level alpha, that's the probability of making a type 1 error. But when we say the probability of a type 1 error, we mean a type 1 error in one test. But we're actually doing 3 tests here, right? We're comparing before to after, we're comparing before to none, and we're comparing none to after. So we're not just interested in the type 1 error rate for one test, we want to know the likelihood of making at least one type 1 error. And this is called the experiment-wise type 1 error rate. Sometimes you also hear it called the family type 1 error rate. And this is the probability of making at least one type 1 error when you're conducting multiple tests of significance. So there's actually a way to adjust your confidence intervals and p-values to get around this problem. And it's called Tukey's HSD. And HSD stands for honest significant difference, so sort of throwing a little bit of shade at the t-test approach. And the benefit of Tukey's is that it adjusts for these multiple comparisons. So we have a problem with our type 1 error rate, and we want to adjust our confidence intervals and our p-values to account for that. So these are still 95% confidence intervals, but here when we say 95% confidence, we're referring to all of the intervals at once. So we're saying we're 95% confident that all of the intervals capture the specified parameter. So usually 95% confidence would just apply to one interval. Here we're saying we're 95% confident all of the intervals do what they're supposed to do. So they capture the parameter that they were going for. And the other thing that this does is that instead of looking at the probability of one type 1 error, it looks at the probability of at least one type 1 error. So it basically adjusts the p-values so that the probability of at least one type 1 error will be alpha. So we're going to come back to this later and talk about how it works. But there are some benefits to using Tukey's HSD because you have a confidence level that applies to your whole data set, and you also control your experiment-wise type 1 error rate, making sure that the probability of at least one type 1 error is just equal to alpha.